In 1962, a cave explorer named Michel Sief started a series of experiments where he isolated himself underground for months without light or clocks. He attached himself to electrodes that monitored his vital signs and kept track of when he slept and ate. When Sief finally emerged, the results of his pioneering experiments revealed that his body had kept to a regular sleeping-waking cycle. Despite having no external cues, he fell asleep, woke up, and ate at fixed intervals. This became known as a circadian rhythm, from the Latin for about a day. Scientists later found these rhythms affect our hormone secretion, how our bodies process food, and even the effects of drugs on our bodies. The field of sciences studying these changes is called chronobiology. Being able to sense time helps us do everything from waking and sleeping to knowing precisely when to catch a ball that's hurtling towards us. We owe all these abilities to an interconnected system of timekeepers in our brains. It contains the equivalent of a stopwatch telling us how many seconds elapse, a clock counting the hours of the day, and a calendar notifying us of the seasons. Each one is located in a different brain region. Sief, stuck in his dark cave, relied on the most primitive clock in the suprachiasmatic nucleus, or SCN, of the hypothalamus. Here's the basics of how we think it works, based on fruit fly and mouse studies. Proteins known as CLK, or clock, accumulate in the SCN throughout the day. In addition to activating genes that tell us to stay awake, they make another protein called PER. When enough PER accumulates, it deactivates the gene that makes clock, eventually making us fall asleep. Then, clock falls low, so PER concentrations also drop again, allowing clock to rise, starting the cycle over. There are other proteins involved, but our day and night cycle may be driven in part by this seesaw effect between clock by day and PER by night. For more precision, our SCNs also rely on external cues, like light, food, noise, and temperature. We call these Zeitgebers, German for givers of time. Sief lacked many of these cues underground, but in normal life, they fine-tune our daily behavior. For instance, as natural morning light filters into our eyes, it helps wake us up. Traveling through the optic nerve to the SCN, it communicates what's happening in the outside world. The hypothalamus then halts the production of melatonin, a hormone that triggers sleep. At the same time, it increases the production of vasopressin and noradrenaline throughout the brain, which help control our sleep cycles. At about 10 a.m., the body's rising temperature drives up our energy and alertness, and later in the afternoon, it also improves our muscle activity and coordination. Bright screens at night can confuse these signals, which is why binging on TV before bed makes it harder to sleep. But sometimes we need to be even more precise when telling the time, which is where the brain's internal stopwatch chimes in. One theory for how this works involves the fact that communication between a given pair of neurons always takes roughly the same amount of time. So neurons in our cortex and other brain areas may communicate in scheduled, predictable loops that the cortex uses to judge, with precision, how much time has passed. That creates our perception of time. In his cave, Sief made a fascinating additional discovery about this. Every day he challenged himself to count up to 120 at the rate of 1 digit per second. Over time, instead of taking 2 minutes, it began taking him as long as 5. Life in the lonely, dark cave had warped Sief's own perception of time, despite his brain's best efforts to keep him on track. This makes us wonder, what else influences our sense of time? And if time isn't objective, what does that mean? Could each of us be experiencing it differently? Only time will tell.